Okay, we have started.
So I will, yeah.
Good evening. Hope everyone is having a pleasant weekend. This morning, we witnessed a brilliant lecture by Dr. R.V. Jadhav from Ridgecrest University, who explained on Coulomb stress modeling and seismicity varying. So it is the time for the second lecture of the day, which will be presented by Professor Susan Hough from USGS. She is the fourth speaker to represent USGS after Professor Michael, Professor Muni, Professor Nicholas. Professor Muni has in fact laid down 3 research problems and nominated prizes for them, which are C.V. Raman Prize, Chandrasekhar Prize, and Rabindranath Tagore Prize. I am sure many of you are preparing your entries for the prizes. Let me remind everyone that all the lectures are recorded and can be viewed via official YouTube channel of our institute, that is CSR-SRTP. The link of each lecture is typically shared in the WhatsApp as well as in the Telegram group. Now, before starting this lecture by Professor Susan Hough, may I request our session co-chairperson, Dr. Saurabh Barua, for his initial remarks. Over to Dr. Saurabh Barua.
Thank you, Dr. Santanu. Today is the 5th day of International Virtual Seminar, and we heard lectures from eminent personalities, as you have already mentioned, about Andrew Michael, Walter Mini, Professor Ramesh Singh, Nicholas, and Professor Gurjit. Today, a very important topic will be covered by Professor Susan Hough from USGS, that is on ground motion parameters for seismic hazard assessment. The ground motion parameters is one of the most important findings towards seismic hazard assessment, because it starts with the ground, it starts with the earthquake, it starts with the P wave, S wave, wave trends, the soil lithology, the ground amplifications, and these ground motion parameters are the prime input for seismic hazard assessment. As I mentioned in the very beginning of this seminar, that entire basic research are inclined to answer one particular question towards earthquake resilient society, which is nothing but seismic hazard assessment. So with the knowledge and understanding over the past few decades, Professor Susan Hough from USGS has contributed immensely towards seismic hazard assessment. We are really fortunate to you have here in this forum to deliver this international workshop, virtual workshop, where 30 countries are participating right at this moment. Will be highly benefited from your lecture, because we are eagerly waiting to hear your lecture. So with that initial remark, I welcome you on this auspicious occasion on behalf of Council of Scientific and Industrial Research of India, and in particular Northeast Institute of Science and Technology. So thank you very much for our invitation. Over to Dr. Santanu Barua.
Thank you, sir. Now let me read out a short biodata of Professor Hough. Professor Hough is going to give a lecture on earthquake ground motions and damage, the long and the short of it. Professor Hough is a seismologist at United States Geological Survey in Pasadena, California, and scientist in of the office. Subsequent to 2010 Haiti earthquake, she led USGS team to install seismic stations and accelerometers. Her team deployed portable seismometers for recording aftershocks of the earthquake, and she continues to cooperate with the Haitian seismologists for setting up of permanent seismic monitoring in their country. She graduated from the University of California, Berkeley, and earning her PhD in geophysics from the Scripps Institution of Oceanography in 1987. She is an avid writer, which is reflected by the fact that she has authored more than 100 peer-reviewed research publications and is the author of 5 books. She has written numerous articles for mainstream publications such as Los Angeles Times. She has served as an editor and contributor for many journals and is a contributing editor to GeoTimes magazine. She has served as the board of directors of the Seismological Society of America from 1998 to 2004 and of the Southern California Earthquake Center from 2006 to 2009. I'll conclude here and request Professor Hough to take over. Looking forward to an interactive participation from all the attendees. Thank you. Over to Professor Hough.
Great, thank you so much for the kind introduction. I would like to start by congratulating the organizers of this very successful symposium. A lot of things in the United States are still shut down, but this symposium illustrates how we can use available technologies to reach people in new ways and exciting ways. And we've had some problems with my bandwidth this morning. So once I wanted to have my video on to say hello. I'm going to turn it off. I think that will, and share my screen. And with the video off, I hope that the sound quality will be okay. So let me share the screen. And okay, I have to do this in the right order. Okay, can you see my screen?
Yeah.
Yes.
You can.
Yes.
Okay.
From mobile.
You can see.
Yes.
So the other thing I need to say is that one of the hats that I wear for the USGS is the Pasadena Earthquake Response Coordinator. And last night, about 11:30 local time, we had a magnitude 4.5 earthquake that was maybe 20 or 30 kilometers from my house. So it woke me up, and I was on the computer with colleagues to pull together information until 3 o'clock in the morning. And now it's 7 o'clock in the morning in California. So this, I'm probably not quite at my best right this second, so I apologize. Also, I realize this seminar is on geology and tectonics, and as you heard in the introduction, I'm going to be talking about earthquake ground motions. So it's not focused on tectonics per se, but it is indeed a very important issue for earthquake hazard. Earthquake hazard maps require really 3 ingredients. You have to understand the potential earthquake sources, and then you have to understand how the how the ground motions will travel through the crust, and then you have to understand what happens to the waves once they hit the shallow geological structure. And so that last part of it is very important. I'm going to be talking about that. And then also, this is a tutorial. I understand that there's a big audience of students. I don't know what people's background is, so if you work on ground motions, some of this will probably be very basic. But I wanted to start at the beginning. So with that introduction, and if you have problems hearing me, or if people have urgent questions, maybe find a way to let me know. Okay, so everyone can still hear me. Yes?
Yes, very much.
Okay, good. So this is the Los Angeles area. where I live, and whoops, okay. It's as is the case for a lot of metropolitan areas. Much of Los Angeles sits in the in a deep basin. So you can see the mountains, and then you have sediments within the basin, and you have some other valleys. And so what we site response, how the shaking is going to vary because of this geology is a very important issue for Los Angeles and then many cities around the world. So an outline of my talk, I'm going to do a brief introduction of what we mean by site response. I'm going to talk about path effects, intensity, and then I'm going to talk about what we call topographic amplification and pervasive nonlinearity. A lot of jargon in ground motions. If you start to read papers, this is a partial list. The basic definition is site response is the effect of local geology on ground motion, and that's what this talk is about. I'm going to be talking about intensities, and commonly we use modified Mercalli intensity in the United States. In Europe and India, people sometimes use the EMS scale, which is mostly equivalent. Let's see, and then HVSR is a method that people use to study site response by looking at the ground motion and comparing the horizontal to the vertical shaking. And it's probably not too important to go through all of these because you're not going to remember the whole list. But if you have this presentation, hopefully it's useful. PGA, peak ground acceleration. Let me just hit a few of them. GMPE is a ground motion prediction equation. So that's an important it's an important term, an important idea. So for a hazard map, the way that hazard is calculated is that you use the forecasted earthquakes and you calculate what their shaking will be using a GMPE, ground motion prediction equation. Sometimes these are called by other names. For example, an attenuation relationship, you might hear that. And let me skip some of the other ones that aren't quite so important for now. But when I use a term, I will try to remember to be clear about what I'm talking about. So I wanted to start with just a few words about intensities because it's an old idea, but it remains a very important one, and it's going to come up throughout this talk. So the idea, I'm sure you know, an earthquake magnitude is a number that tells you what the size of the earthquake is. But the magnitude scale was only introduced in 1935 by Charles Richter. Before that, there was no way to measure the size of an earthquake, but people used intensities, numbers to describe how strong the shaking is in any place. And I'm sure you've seen this before. This was pioneering work by Robert Mallet in 1857, and he had his own scale, but strongest shaking and then less shaking. So this is an intensity map. So this is an idea that goes back to the 19th century. But intensity remains very useful even today. If you've seen maps like this one on the right, which is kind of like a USGS shake map, that is showing you intensities. So this modified Mercalli intensity, essentially this old scale that's been in use for 100 years, where the red colors are intensity 9, that's very damaging. 6 to 7 is yellow and orange. That's 7 is moderately damaging shaking, and then at the other end, my cursor's being funny. The purple is intensity 2. That's shaking that's weakly felt. So last year we had a magnitude 7.1 earthquake in the desert. So it's California. This is the desert is up here. Los Angeles is down here. the earthquake was felt over most of California and into neighboring states. And again, this map is showing, it's not showing peak ground acceleration, it's showing intensity, because this remains a very useful way to convey the information. If you want to know how strong was the ground, how strong was the shaking, where was it felt, we revert to intensity. But what we've learned in recent decades is that these intensities, so these intensities come now from an online system, the Did You Feel It system, where people go to the internet and they fill out a questionnaire about whether they felt the earthquake, whether there were effects or damage, and then an intensity number is calculated. So we get a lot of information very quickly to make a map like this. So you can take that information that people, the intensities from what people report. So these are not instruments, and you can calculate from those intensities, you can calculate peak ground acceleration. And that for the Ridgecrest earthquake on the left, as a function of JB distance is the distance to the fault at the surface. So if you take the intensities and convert to peak ground acceleration, you get these black diamonds. And then if you take the seismometers and accelerometers and look at the PGAs that are recorded, you get these squares. So what you can see from this is that intensities coming from what people tell us about shaking are very, very, very consistent with what you measure on a seismometer. So we can use this intensity data even now to investigate earthquakes. And then the line here is the prediction for magnitude 7.1 using a modern ground motion prediction equation for California. So that was a lot. That was just some introduction to explain what maps like this are showing, and to make the point that you can use either intensity data from eyewitnesses or seismometer data to generate maps like this. And so you're going to see maps throughout the talk that use both. So now let me talk about site response. And so this is a sort of a somewhat famous figure by now, from work that I did as a postdoc after the 1989 Loma Prieta earthquake, which occurred down here. This is the San Francisco Bay Area. I don't have a bigger map, sorry. And then if you come up here to Oakland and San Francisco, there was quite a bit of damage. And then around the bay, there are very soft sediments. So this sort of illustrates the textbook idea of site response, that you have, I installed portable seismometers in the hills, so on bedrock, versus alluvial sediments, versus very soft sediments by the bay. And you can see this is an aftershock 80 kilometers away, so the same distance essentially, but you can see how much stronger the shaking is on the soft sediments and intermediate on the alluvial sediments. So this is the textbook view of site response, that you get more shaking on softer sediments. I'll talk about soft in a second. And there was a two-deck freeway that was built over the very soft sediments, and it collapsed. And so there were quite a few fatalities associated with this collapse. So the physics of site response are very basic. The equations are well known. The idea is that you have the fault, the waves propagate, and then if you have soft sediments, and by soft we mean low impedance. So impedance depends on the shear wave velocity and the density, but we usually just consider the shear wave velocity as a proxy for impedance. And let me go on to the next slide. That's useful. So, oh no, go back. Okay. No, it's in two slides. Okay. Sorry. Okay, so the energy comes along, and because you have a low impedance layer, you get amplification by conservation of energy. If you have a sharp contrast in impedance, it gives rise to resonance effects, and I will talk about that in a second. Okay, so frequency is a very important concept here. I don't know if people have had introduction to Fourier spectra and spectra analysis, but it's a fairly straightforward concept. Earthquakes release energy over a wide range of frequencies or a wide range of wavelengths. You can think of an earthquake like a musical symphony that has a wide range of tones, from low tones to high tones. So we use spectral analysis to consider the energy at different frequencies, because for building damage, it's very important, not just the amplitude of shaking, but what's the frequency of shaking, and I'll talk more about that. And site response is strongly frequency dependent. So this is just a picture of a light spectrum, which I'm sure you're familiar with. It's the same idea that the white light is made up of many different wavelengths, and the prism here is breaking that energy up so we can see the different frequencies. So I just wanted to mention that concept. So I'm going to show a number of plots like this, which are plots of as a function of frequency. So we talk about the frequency domain. You can look at a seismogram in the time domain, just as the record as a function of time, or you can use spectral analysis to break it down in the frequency domain. So we're plotting here as a function of frequency from 0.1 hertz out to 100 hertz. And typically log axes are used. And so this figure is showing site response. So the idea, the very basic physics, is that you have a wave that's coming in. It's going to be diffracted if you have a velocity contrast, and it's going to start to reflect. And if this material has a much lower velocity than this layer, you set up a resonance. The energy gets trapped. You can look at the problem in, I think the next slide shows in one dimension, or sometimes you can look, the problem becomes two-dimensional or three-dimensional in some cases. So this figure shows, what a resonance, a site response resonance looks like. You trap energy at certain periods or frequencies, and you get a resonance peak. And if another term to introduce is what we call Q. So Q is a quality factor that describes how energy is attenuated in the material. So if you had no Q, if energy was not attenuated, you would get resonance. You'd get a fundamental peak from the resonance, and then you would get what we call overtones. That comes out of the mathematics that I'll show you in a second. And if you didn't have any attenuation of high frequencies, this would just go on forever. But in the real Earth, we have attenuation. So the site response, the theoretical site response, looks like the green curve or the red curve. So a fundamental resonance mode, and then typically some overtones. So the equations, this is a terrible slide. I don't want to go through the equations. This is for the 1D case, where you have a vertical wave coming in and a contrast in impedance, and then you trap the energy. So I showed this slide to show you that you can solve these equations analytically for the one-dimensional case, and you can make the predictions, and then you can also For two-dimensional cases, you can also solve analytically, and then for more complicated three-dimensional cases, typically you can solve numerically. So the point is that the physics are well known of what happens when energy comes in and you have a layer of soft sediments. So to estimate site response, there's a number of approaches that we use using recorded data. You can make predictions of site response if you know what the velocities are. If you know that there's a sedimentary basin and you can estimate the velocities, you can predict site response. The most straightforward method to estimate site response is spectral ratios. So if you can record shaking in a valley compared to shaking on hard rock, you look at the ratio of, and again, typically in the frequency domain, so as a function of frequency, and get site response. There are other methods as well. One is by looking at the horizontal to vertical ratio with this HVSR. So you can do that using earthquakes. Some people, you can also report ambient noise and look at the ratio, and this gives you some information that can help constrain site response. And then if you have a lot of earthquakes recorded at a lot of stations, you can set up what we call a joint inversion and mathematically take that data and solve for the earthquake source effects and the path effects and the residuals or the site response. I just want to list that. So this is how site response estimation has been done in California fairly recently. So I've talked so far about the effects of having near surface materials that are softer, that have lower velocity. There's a second effect which has to do with the basin depth. So we know when you have deep basins, that also gives you a deep amplification effect. And when you put those two together, you get a map like this one. So this is the LA basin turned on its side, which shows the amplification. So let's look at this one. This is this was done 20 years ago now, but it's a map showing the amplification across the Los Angeles basin. So this is Los Angeles. You can see that there's quite a bit of amplification predicted. And then LA Basin, you have valleys. Now one key point for my talk is if you look at this map, it suggests that the worst shaking is going to be in these yellow areas. That's where the strongest amplification is going to be. But I've explained that amplification depends on the period of shaking. So if you think about, and this map, it doesn't tell you what period of shaking. Is this amplification at 10 hertz? Let me see if I can get my camera back on just to, I'm not sure this is going to work because I can't see myself. But this is actually a map that's calculated for shaking at 1 second period. This is ground motions that go back and forth in 1/1000. If you think about what the ground would sway back and forth, 1/1000, that's fairly slow. Okay, it's saying I have a bad network quality. Can people still hear me? Hello? Hello? Can people hear me?
Yes.
Okay, I'm getting a message saying I have a bad network quality. Okay, so
no problem.
Okay, so yeah, this map is 1 second, and if you think about what that ground would feel like, that's fairly slow. But that's what this map is showing, the amplification at that fairly slow back and forth period. So I will get back to why that matters. Oops, find the right button to push. So yeah, now let's talk about building response. So how does a building respond to shaking? And again, if you've had engineering seismology or engineering, this is going to be very basic, but I wanted to cover the basics. If you have a structure, it's going to have its own natural period. So any structure will tend to sway back and forth at some period that depends on the size of the structure. And what shaking is damaging when the ground is swaying back and forth at the same frequency as the building naturally shakes. So you can think of a child on a swing who's going back and forth every few seconds. And if you pushed too frequently, it wouldn't cause him to swing. But if you pushed every time he swung back, that's how you would make him swing higher. So a building is going to shake when the ground is pushing it at the frequency that it naturally sways at. And as a rule of thumb, every building has its natural period, the period or frequency that it tends to sway at. It's about 0.1 times the number of stories. So a 10-story building tends to sway back and forth at 1 second. If it's a 1-story building, it tends to sway back and forth at 0.1 seconds or 10 hertz. So that's a big difference. This map that I'm showing you is the amplification that will be most damaging to 10-story buildings. If you think about a small building that's sitting and you shake it back and forth at 1 second, it's not so affected because you're not putting a lot of energy into the structure that in a way that it will even respond to. So when you look at an intensity map, you'll see these commonly. This is the map from the Ridgecrest earthquakes. I told you that these intensities provide a good measure of what you see with a seismometer, but this is data from people. And people generally don't live in 10-story buildings in California. The typical house is more like this. It's 1 story. This is the house that my grandparents built in Ridgecrest in 1964 when I was 3 years old, so I know it well. But an intensity map is not showing you shaking at 10-second period. It's showing you what the shaking is at the frequencies that affect houses like this mostly. It's showing you shaking at maybe 3 hertz to 8 hertz. So there's already a disconnect. This map shows you what's going to happen at 1 second period, whereas this intensity map, in the maps that we look at, are not at 1 second period. They're showing you the shaking at higher frequencies. So that turns out to be quite important. So again, you have site response and you have building response. So tall buildings are affected by long period energy. Typical buildings are affected by 3 to 8 hertz energy in that range. And so the intensity maps that we put together and that I've shown you are reflecting this higher frequency and not this. Okay, so now let me talk about, I'm going to go on, and that's sort of the basics of site response, the textbook ideas. I'm going to go, for the rest of the talk, I'm going to talk about more complicated factors that are important for site response. So the first of them is 2-dimensional and 3-dimensional wave propagation effects. This is an old figure from work by Kim Olson. So this is the Southern California area, and this is looking at theoretical predictions of how the Los Angeles basin will respond to earthquakes on different faults. And what you can see with simulations is if you have a deep basin or deep valley, the response is going to be quite different depending on where the earthquake source is, because this is not a 1-dimensional problem, it's a 3-dimensional problem, and how the energy comes into the basin makes a big difference. So if you come down, I know that this isn't the best figure, but it's a nice set of results to illustrate the point. These bottom two plots show the predicted site response for the same earthquake, San Andreas Fault rupture, the same San Andreas Fault rupture, but changing the direction of rupture, the directivity. So you see that the LA basin has quite a different response, just depending on how the energy comes in. Even if you specify which fault is going to break, it's a strongly three-dimensional problem. So this just shows, I wanted to show a movie, but I was having problems including it. This is a map of shaking intensity from an earthquake that happened in Los Angeles in 1933. So this is California, Los Angeles. The 1933 Long Beach earthquake was quite damaging. We don't have a lot of information, but this is a project I did recently to describe what the shaking was like from a few instruments and then the damage pattern. And so the fault that broke, the epicenter was here, the earthquake ruptured here. What you can see here is these high intensities in this area. And so that's a three-dimensional, you can explain that with computer simulations it's a three-dimensional effect. So you have the Newport-Inglewood fault here, and it's associated with a discontinuity in velocity. So on this side, the LA basin is deeper than on the west side. So the energy comes off the fault and it's channeled up into the LA basin, and so that caused quite high damage. So this is a three-dimensional effect that's not described by the simple textbook site response models that I took you through. Okay, so that's just briefly path effects, which can be quite important and difficult to predict because they are so strongly three-dimensional. So now let me talk about topographic amplification. So the textbook view of site response is that shaking in sediment-filled valleys is stronger than shaking on hard rock. Hard rock shakes less. But then there are some cases where you get amplification on hard rock, and this work came out of a project I was involved with in 2010 after the Haiti earthquake, which was a very devastating event. There were no seismometers in Haiti at the time of the earthquake, so USAID supported me and a small team to go in and install seismometers to record aftershocks. And these are some of my colleagues from the USGS and then from Haiti that I was working with. So this is Port-au-Prince in Haiti, and it is a sedimentary environment, for the most part, a former marine environment, and you have hard rock to the south. There's a mountainous area to the south of Port-au-Prince, and then you can see the port area, central Port-au-Prince. And the colored maps show a damage proxy map from the earthquake, where orange is quite severe damage, yellow is moderate, tan is light damage, and then there's no data. It's clear. So we installed 6 seismometers in this area on hard rock, in the foothill area, and then in the central part of the valley. You can see them here. So this seemed similar to the 1989 case that you had. I turned it on its side. So this is Oakland, this is Haiti. But in both cases, you have hard rock, and then you have older sediments, and then you have softer sediments. So the expectation was that the strongest shaking was going to be where you have the softest sediments. But in fact, let's see, what's the best place to show it? In fact, Port-au-Prince, there's a foothill area. There's a pliomiocene fan complex that has a lot of small-scale topography. So this isn't just a mountain and a flat valley. It's really mountains, foothills, and valley. And so this is what the aftershock recording showed. So the main shock was over to the west of Port-au-Prince here. And then looking at this line of stations, this is the hard rock below. This is the center of the valley. The strongest shaking that we recorded was not in the center of the valley, but at these foothill stations, which is not what the textbook ideas predict. Okay, so this is, I should have shown this first. This is a geologic map of the Port-au-Prince region. You can see the harder rock. This is this fan complex that I mentioned. So a fair amount of the city is actually built on it with these small hills, and then the alluvial sediments are the pinkish color. Okay, so it turns out that topography was giving rise to amplification. If you take the damage proxy map and drape it over topography, so this is looking, it's sort of a funny angle, but you can see there's quite a steep ridge in southern Port-au-Prince. The Hotel Montana, if you remember hearing about that collapse, sits here right at the top of the ridge. And the damage followed the topography. So, and then I think I have another example. Yeah, so this is another part of the city. This is towards the airport, a little bit to the north. There's small hills here, and you can see again that the damage was concentrated right where you have that small scale local topography. And you can look at it with profiles in different ways. You could see it driving around town. The construction quality is generally poor in Haiti. That's why there was so much damage. But preferentially near these small hills, it was much worse. And so this is, whoops, okay. This is what we call topographic amplification. I didn't include a slide, but if you think about a small hill or a ridge, energy can also get trapped in a topographic feature. It's almost like a building response. If you shake a hill, it's going to have its own response, potentially its own resonance, and that can give rise to amplification. It depends on the size of the hill, for example, what frequencies are going to be amplified. So it's a hard rock effect. It's not a consequence of having soft sediments, but it can also be very important for the distribution of shaking. Okay, so the last thing I wanted to talk about is what we call pervasive nonlinearity. Okay, what do I mean by that? I'm going to talk about some results from the 2015 Nepal earthquake and the recent Ridgecrest earthquakes. So you probably, sure you've heard a lot about the 2015 Gorka earthquake, magnitude 7.8, 7.9. It occurred to the west of Kathmandu. It ruptured the plate boundary, the main Himalayan thrust, as you can see in this cross-section. And the rupture extended essentially to right underneath the Kathmandu Valley. Kathmandu is a former lakebed zone, so it's full of sediments. And it's a place where we predicted that there would be quite a lot of site response if an earthquake happened. So then this earthquake happened, and it seemed like a worst case for Kathmandu, magnitude 7.8, almost directly below the lakebed zone. If you've been to Kathmandu, you know what it looks like. So this is the lakebed zone. It's very densely populated. Okay, well, after the earthquake, I visited about a month after, and this is what a typical street scene looked like in Kathmandu. You can see the typical construction, and for the most part, a month later, it was, in many places, you couldn't tell that an earthquake had happened. This was pretty stunning. That knowing, I think you can tell the buildings are not always such good quality construction. Some of them are, but a lot of them aren't. You would, in a magnitude 7.8 earthquake directly under the valley, we would have expected a much worse outcome in terms of damage. The biggest change after the earthquake was that the traffic was so much lighter because people had gone back to the villages. Now, the earthquake overall killed 9,000 people, so that was a very heavy toll for Nepal. There was a lot of damage in local villages, but in Kathmandu, the effects were a lot lighter than a lot of people had expected. There were some pockets of damage. This is the Swayambhu Temple, Monkey Temple, and you can see the heavy damage to older buildings. This is the Swayambhu sits on top of the highest local hill in the valley, and so I haven't done any analysis of this, but it seems pretty clear that this was a topographic effect. That the damage here was much stronger than other parts of the valley, and that's consistent with local amplification due to the hill, so this topographic amplification. But then what happened in the valley? Why wasn't there more damage due to the amplification? Okay, so let's see. This is what there was. There wasn't a lot of seismometer data or accelerometer data from the earthquake, but there was a little bit. And this shows the north-south component of shaking in the Kathmandu Valley as a function of time, and so you can see these big swings going back and forth. And this is about a 5-second period. So the ground in Kathmandu during the main shock was going back and forth, 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000. It was sloshing back and forth quite slowly. And then there's more complexity here. If you integrate this to get to displacement, this is how the ground moves. So the Kathmandu Valley moved about 1.5 meters to the south in this as a consequence of this earthquake. Okay, I keep forgetting which. So okay, to understand the shaking and what was going on, we turn largely back to these intensities. So this is a blow up of this blue outlines one estimate of the earthquake rupture itself. So the earthquake started here, it ruptured in this direction, and then the square shows the Kathmandu area. And so this is a map that's put together from shaking intensities from observations of building damage. And you can see that there are some intensities up to 9, but this is in the Kathmandu area. Just on this map, you can see that it's not reds, it's mostly yellows. It was actually intensity 6. So that this reflects that low degree of damage in Kathmandu. So again, a magnitude 7.8 earthquake. It was about 12 kilometers of fault below the city, and you're only generating intensity 6 shaking. Another way to see that more clearly, if you take this intensity map and subtract out a baseline, you can look at the residuals. So, you can compare this to a map of the predicted shaking and look at the residuals. So where was the shaking relatively high or relatively low compared to what we would expect? So this is a map of residuals. So now purple is where the shaking was lighter than expected, and red is where the shaking was greater than expected, and green is shaking that's about the level that we expect. So if you come into the Kathmandu Valley and break that over topography, what you can see is purple. In the middle of the Kathmandu Valley, the intensities were lower than expected in the valley, not amplified, not like the simple models predict. So if you look at the available accelerometer data that were installed by a Japanese team working in collaboration with a local Nepali team, you can look at the shaking at sediment sites in the valley compared to a reference site on hard rock. So these are these spectral ratios. And I think, yeah, so this is, there's 4 stations. There were 4 stations on sediments and then 1 station on hard rock that you could compare. So let me zoom into this one. It's fuzzy because I've zoomed in, but hopefully I can sort of take you through it. So this is plotting the energy as a function of frequency from 0.1 hertz out to 20 hertz. And this is looking at the site response estimated from a spectral ratio. So again, you're comparing the sediment site to the rock site. If they were the same, you would get 1. This is the line. So it's a log-log axis. This is showing both a 6.6 and a 7.8. But let's just look at the 7.8 shown in red. And what you see is this is the site response curve, which does look like the prediction I showed you at the beginning of the talk. You get quite strong amplification up to a factor of 10. But then when you get out here, which is about 2 to 3 hertz, all of a sudden the sediment the shaking at the sediment site is lower than shaking at the hard rock site. And this is what we call a pervasively nonlinear effect. So you may have heard of nonlinearity, like liquefaction is when you shake sediment so hard that they stop acting like an elastic solid and you get deformation. This is not liquefaction. This is a more of a grain scale phenomenon. When you shake sediments, loose sediments strongly, they also stop acting like an elastic solid. You get adjustments at the grain scale level, and that's a process that actually absorbs energy, and it absorbs the high frequency energy. So this is nonlinearity. Basically means that this is a different response because it's strong shaking than what you would predict if you shook the same station with much weaker energy. So this is another very important complication from the textbook models. The textbook models didn't consider how strongly the ground shook. They assume that the amplification would be the same if the ground shakes strongly versus shakes weakly, and that turns out to not be the case. So this is important because if you're measuring site response using magnitude 3 and 4 earthquakes, it's not going to tell you the same story for what's going to happen for the earthquakes that you care about. So this is one of my my favorite pictures of a local structure. I think you can tell that it was built in stages. The construction quality is not so good. You would not expect this to be, you wouldn't expect it to be very resilient to shaking. But if you think back to the discussion about period and building response, this is a 3-story building. And the ground in Kathmandu was shaking, the basin, the valley was swaying back and forth at 5 seconds, 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. It didn't affect this building. That shaking was just too slow, back and forth. And the energy that would have been damaging to it was the more jittery, high frequency shaking. That was actually absorbed or de-amplified. And so that was the important part of the story here, that for why the damage wasn't worse. And then moving on, I think I'm getting low on time. the Ridgecrest earthquakes in 2019. There were actually two earthquakes. One was, the first was a magnitude 6.4. It was on the 4th of July, which is a big American holiday, so it was not very convenient. And then about 30 hours later, we had the main shock, a magnitude 7.1. This part of California is not too densely populated, but there is this town of Ridgecrest, and then the shaking was widely felt. So this is a magnitude 7.1. The town of Ridgecrest is quite close. This shows you, this is a damage proxy map. So this is a map from, the colors show, I probably don't have time to explain this, but you can use satellite imagery, and there are some very nice techniques that have been developed to look at how the coherence of images, satellite images, changes after an earthquake, and you can identify places on the ground that were damaged, either because the fault moved, so this is part of the fault, or because you had rock slides, or because buildings were damaged. So here's this town of Ridgecrest. The earthquakes happened, 15 kilometers away, a magnitude 7.1. And you can see here that you're not seeing very much red and yellow. There was very little damage in this town, which is quite close to the earthquake. If you, let's see, look at, there are some zones here. These are areas where the map is revealing some damage. It turns out that those are not buildings. Those are places where they had old cars or old machinery, mostly, that were moved around by the earthquake, but not building damage per se. So overall, the story was similar to the Kathmandu Valley, that you had this town sitting quite close to large earthquakes, very little damage. And so Ridgecrest is sitting also in an alluvial valley, the Indian Wells Valley, shown here. The earthquakes were just over there. And then, okay, I may go through some of this a little bit quickly. If you look, you can look at what the ground motion, what the predicted ground motions would have been for the 6.4 versus the 7.1, and you can look at the intensity data and the instrumental data to compare what happened versus what's predicted. Okay. So let me focus on the bottom one. This is essentially what I showed you earlier. You could look at the intensities or the instrumental data, and they agree quite well. They agree with each other, and they agree with the predictions. So in this case, the shaking was consistent with predictions from a modern ground motion prediction equation. So it wasn't really a surprise that there wasn't more damage. So this is the town of Ridgecrest. This shows that the intensities were only 6 to 7. Here's the magnitude 7. Here's the magnitude 6.4. This fairly low level of intensities is consistent with these modern predictions. And so if you do the same kind of spectral ratio analysis, you see the same story as in Kathmandu. If you focus on the blue line, so this is again frequency, spectral ratio. The blue line shows the sites black shows the ratio and sediment sites, and you can see, just like Kathmandu, the ratio goes below 1 at 3 Hertz. So it's the same story. The energy at 3 Hertz and above, which would have been damaging to the 1-story, 2-story buildings, was de-amplified. And it turns out that, so you had amplification in it's called the Indian Wells Valley. You get if you go to these longer periods, like Kathmandu, things where the waves were sloshing back and forth in the valley. So there was that amplification, but this would have affected tall buildings. And there aren't any tall buildings in Ridgecrest, but the high frequencies were amplified. And it turns out, let me just focus on this part, the modern ground motion prediction equations that we have for California include nonlinear terms. So they're constrained by quite a bit of global data, and they capture this behavior. So that's why the shaking wasn't a surprise. And I'm going to skip over some of the details on this. But because you have these good, modern, well-constrained ground motion prediction equations, you're actually doing a good job of predicting this nonlinear behavior. And this is a major issue for the Indian subcontinent. The GMPE development is still ongoing. They're not very well constrained by recordings of large earthquakes at close distances. And so this shows you the shaking intensities that you'd predict as a function of distance from the fault. This is a relationship in California, magnitude 5, 6, 7, 8. And what you see is this saturation, that from magnitude 5 to 6, you get a big jump in the predicted shaking intensity at close distances. But if you go 6 to 7, 7 to 8, the intensities and the peak accelerations don't increase that fast, and that's a consequence of this nonlinear behavior. So the challenge for India, Nepal, and many parts of the world is that you don't know what these curves look like for large magnitudes. You've only recorded moderate earthquakes, or maybe you've recorded bigger earthquakes at some distance, like the Gorkha earthquake was recorded at some stations in northern India. What you really need to know is what the shaking level is going to be close in for big earthquakes, because if you predict it and you don't have data here, you tend to over-predict in the near field. Okay. So yeah. I think if students out there are interested in a problem that has a lot of practical importance and gets into some interesting seismology, again, this ground motion prediction equation for India, it's a quite complicated problem because you have earthquakes that are occurring along the Himalaya. You have very different paths in different parts of the region. And I'm sure work is ongoing. I'm sure there's more results than I've seen, but because the data are limited, it's been a very challenging problem to develop good modern ground motion prediction equations. So just to conclude, try to summarize everything I've talked about, we know that basins and valleys, large-scale basins and valleys will give rise to amplification. It's generally at quite long periods. Where you have soft, shallow sediments, you get amplification for weak motion. So small earthquakes, you get amplification according to the physics that I talked about at the beginning, but for strong shaking, for strong motion, you actually de-amplify those frequencies, which can be very important. At hard rock sites, you can, depending on the local topography, you can get these topographic effects that are hard to predict because they're very complicated and they depend on the details of the structure, but they can be locally important. And if you want to predict the shaking intensities, you need to have good ground motion prediction equations that are well constrained by large earthquakes critically at short distances. Because if you don't have that data, the predictions may be too high. So the textbook images are here. This is what shallow site response looks like. This is what deep basin response looks like. The textbooks aren't wrong per se, and these phenomena are well understood. The physics are straightforward. We have quite a bit of observation. But the point is that the real world is quite a bit more complicated than the textbooks. And in particular, the site response, you can't consider it by itself. You have to think about what the site response is compared to the buildings that are exposed and how they are going to respond to shaking, because that's what, in the end, that's what matters. So with that, I will thank you for your attention. I hope that was clear. Let me see if I can get back. Okay. Oh. Good to
Thank
see
you very much. Thank you very much for your attention-getting talk. You discussed about the recent research that illustrates how the physics of the wave propagation can be more complex than the simple models. Now, may I request our session chairperson, Professor J.R. Kyle, for his remarks. Over to Professor J.R. Kyle.
Oh, thank you, Shantanu. Thank you so much, Susan. Nice to see you.
Yes.
I'm sorry that I missed a little bit, not little bit, maybe half of your lecture. I could join you at 8 o'clock in Indian time, so I missed a lot. But as usual, your lecture was so magnificent, so so enlightening. It was amazing to see that the textbook type of side response, what we study, the hard rock is less amplified and sediments is more amplified. So that means that side response is not really indication of not the true picture of the actual happening, how it will behave for a large or great earthquake. Means that depends on the ground motion, as you said. That was really interesting. I was so fascinated to see that. So lastly, you conclude that, well, you can do site response study, but you have to consider what type of building and how many storied building is sitting on that site. So in spite of your site response data, the building may fail depending on its natural frequency and depending on the ground shaking and depending on the frequency of that ground shake. So all these things really enlighten us, and we are so grateful to you for such a delightful lecture, and you are always a good teacher. I think we all enjoyed, and thank you so much, Susan, for joining us. It was a wonderful lecture, and I give it to Shantanu, for, I think some questions will be there, and we will be listening to your responses to the questions of the participants. Thank you, Susan. Thank you again.
Thank you.
Thank you, sir. Now, may I request?
There is an important implication here that you have this long period site response, say in, let me turn off my picture. So you have this long period response in Kathmandu or Ridgecrest. So in Kathmandu, that shaking would have been damaging to a 50-story building. But there are no 50-story buildings in Kathmandu. In Ridgecrest, shaking would have been damaging to a 30-story building. So there is an opportunity, if seismologists can understand this long period shaking, it leads to a recommendation that you limit building heights. You don't want to start building a 50-story building in the Kathmandu Valley for the next earthquake. It's good to keep the structures smaller.
Thank you, ma'am. Now, may I request Dr. Saurabh Barua for his remarks. Over to Dr. Saurabh Barua.
Well, I'm just speechless about the lecture, what you have delivered. Professor Susan Hough touched upon the impedance contrast and its amplification. And when amplification is concerned, that is itself indicates the site response. And she said about it's really challenging to all of us in India as well as other parts of the world to derive a ground motion prediction equation, what we call as GMPE, because it is site specific, it is ground motion dependent. So all these things she has touched upon, and we are really enlightened with this contribution of yours, and I am really thankful. We are really thankful for accepting our invitation to the August gathering, what you have delivered. Over to Dr. Shantanu.
Thank you, sir. Now, may I request Prasithya Pathakar for the question and answer session. Over to the Prasithya.
Thank you, sir. Good morning, Professor. With your permission, I am going to read out the questions from the participants' end. So the first question goes by, why we consider VS30 only, not VS20 or VS10 for calculation in GMPE?
Okay, so this is a fairly expert question. I did not introduce VS30, but when we talk about, as the person who asked the question knows, when we talk about soft sediments, low impedance, we use this VS30 so that, and I turn my camera off again, so hopefully the sound quality is better. You have VS30 means the average shear wave velocity in the upper 30 meters, and that's usually the measurement that we have. So what is the site, you know, how do you characterize the site? Are the sediments soft? Is it hard rock? We typically practically use VS30, this estimate. It was a practical choice that it came originally from drill rigs that would drill into the ground to measure near surface properties, and 30 meters is about 100 feet. So drill rigs commonly go down to 100 feet. So commonly we have information down to 30 meters. And so that, because that's the information that people have, people started to look at it and show that VS30 it's a pretty good proxy for what the near surface material is if you have a soft sediment site. But obviously it's just one estimate of what the shallow materials are. And if you think about the physics, you know, VS30, well, you could have a very thin sediment layer, or you could have a very deep sediment layer. So VS30 is not a perfect proxy, and there's a lot of issues, but it's the measurement that we have commonly, and so it's what people tend to use. That's a good question.
Ma'am, the next question is, yes, ma'am.
Well, if there's students out there that are working on this, there's a lot of work, I think, yet to be done to think about how we're characterizing site conditions, you know, and can we improve on VS30? I think there's a lot of room for improvement still.
The next question is it meaningful to consider VS30 in deeper sedimentary areas?
I'm sorry?
Is it meaningful to consider VS30 in deeper sedimentary areas?
Yeah, so that also gets to the limitations of VS30. So you're using just the upper 30 meters, and you know there's a complicated velocity structure. So we typically consider two things separately. We look at what we predict for the shallow response, this VS30, plus the deeper response. We kind of break them into two pieces. So that's what I talked about. You can predict what the basin response is if you know basin depth, and then you can predict what the shallow response is if you know VS30. But that's obviously a very, it's a very big simplification. You would really want to be able to, it's really the shear wave velocity profile that's important, and the three-dimensional structure of the valley. So everything that I talked about is a very big simplification.
Okay, ma'am. The next question is, how should we trust HV amplification ratio? Sometimes it may be underestimating.
Yeah, I think the ambient noise spectral ratio results have always been intriguing. There's been a lot of work done with ambient noise, and some very nice work to map out the period of response and to try to get at the amplification using ambient noise if you don't have earthquake recordings. And so it's an attractive method. I think it's important, but it's not always clear how it corresponds to the earthquake site response. So there's also a lot of work to be done there. It's better to have the earthquake recordings is much more direct information, but it's obviously difficult to record that kind of data.
Tashina Alam wants to know, Dhaka city has areas where rivers and ponds are filled and then constructed upon. What type of site responses can we expect there?
I didn't hear the first part. Can you say again?
Dhaka city has areas where rivers and ponds are filled and then constructed upon. What type of site response can we expect there?
Is the question about artificial fill, places that are filled? Yeah, that typically gives rise to strong amplification as well. So that's, it's an issue like in the San Francisco area. There are places that were around the bay. There's a lot of artificial fill, and that caused a lot of amplification. There are strategies for what they call engineered fill. So apparently, I don't know about the details, but apparently you can, for artificial fill, there are ways to do it that are better for earthquakes. But it's definitely an issue, and we know it tends to be associated with stronger damage.
The next question is, can the probability of an earthquake being determined by going through and summing up the seismograph recordings of various earthquakes occurring in different earthquake belts within a short interval of time, and thereby taking an average probability value?
No, that's the problem is that we don't have enough data. So you would like to know what the full range of earthquake shaking has been for 10,000 years, and then you can give the probabilities of what the shaking would be in the next 100 years. But we have so little data, so we really need to predict the shaking from earthquakes that that haven't occurred. We don't have any data for. There is an idea, we have, I've talked about intensities, so these maps that come from from the earthquake effects. So we have intensity data going back, a few hundred years. And there are ways to look at the intensity data to see how places have been shaken over a few hundred years. And you can use that approach to start to make a forecast, but even then the data, we don't have enough data to really do the job. So that's why we rely on these predictions. It's a very interesting suggestion.
Possibly Mukherjee wants to know, if fluids are trapped in sediments and rocks, how the amplification will vary. Is there any correction for fluid parameters included in your studies?
That's a That's a good question, and the short answer is no. You know, considering the effects of groundwater, it's not generally done. So yeah, that's another. It's an interesting question that more work could definitely be done on that.
The next question is, which earthquake source parameter, example stress drop, frequency, directivity, rupture velocity, mode of rupture propagation, mostly affect ground motion?
Okay, that's a very expert question. So yeah, I know for the students out there that are familiar with ground motion, you know, again, my lecture was probably at a very simple level. But that's, yeah, what controls the ground motion? So magnitude is obviously critical, and distance are the two main effects. How big was the earthquake and how far away how far away were you from the fault that moved? Those are the two big effects, and that's what we capture in a ground motion prediction equation. But if you're familiar with ground motion prediction equations, if you compare data, you see a huge amount of scatter, and they're always plotted on log axes, and the scatter can be an order of magnitude, even for the same magnitude earthquake. So all of those other factors are also they're complicated and they're important. So what's the site geology, like I talked about? What are the path effects? The stress drop, that's a very good question. And let me say a few words about this, because I think it's important and it's not, I think, always understood in seismology. When we now use moment magnitude to describe the size of an earthquake, that is what's reported, at least by the USGS. The moment magnitude depends on the size of the fault that moved and the average slip that it moved. So it's a static measure. How big was the fault? How much did it move? Moment magnitude is not a direct measure of radiated energy. The radiated energy depends on the details of how the fault moved. Was it relatively fast, relatively slow, relatively smooth? And we use, the questioner, I think, knows this, we use the parameter stress drop, which describes the nature of the motion. So you can have an earthquake with two earthquakes with the same magnitude, but if one has a higher stress drop, and that I could talk for an hour about stress drop, but if you have a higher stress drop, if you think about it as a faster earthquake, say, it can release a lot more energy. So moment magnitude by itself is not a good predictor of shaking. It is on average, but I think in terms of what controls the overall shaking level, I think the stress drop of the source is a key parameter, and it's one that we don't talk about very much. And it's difficult to estimate, but yeah, the details of the fault break are critically important for shaking.
More question and stop, I suppose.
Yes, sir, that's all. These are the questions from the participants, ma'am.
That's all. Okay.
Thank you very much, ma'am, for answering questions. Now,
yes.
May I request Dr. Rajkumar for his vote of praise. Over to Dr. Rajkumar.
Thank you, sir. Thank you for giving me this opportunity to propose a vote of thanks in this occasion. Good morning, ma'am. I, Chinmay Rajkumar, on behalf of CSR NIST and our entire organizing committee, convey my hearty thanks to Professor Suzanne Hough for such an informative and informative speech and presentation, and giving us an insight on earthquake ground motion and damage. It is a great honor to have you with us today. Thank you, ma'am. I convey my gratitude to our Director, Sir, Dr. G. Narhaj Sastry, for his support and cooperation to conduct this workshop. My sincere thanks goes to respected Chairperson of today's session, Professor J.R. Kyle, Sir, and Co-Chairperson, Dr. Saurabh Barua, Sir, for their continuous support and guidance. I also thank Dr. Santanu Barua, Sir, for giving us such an amazing platform to interact with such eminent personalities in the field of seismology. Last but not the least, I thank all the participants across the globe for their active participation and all the members of the organizing committee for their tremendous effort and hard work to make this international workshop a success. I thank you all once again. Thank you.
Thank you.
Thank you again to the organizers and to the students, to everybody who tuned in.
All right, ma'am.
Thank you, Susan. Bye-bye. Thank you.
Bye. See you.
Well, sir. Bye-bye. Good night.